You've been running your robot in simulation, and it works perfectly. Nodes start, communicate, and everything flows. Then you deploy to real hardware, press the power button, and the robot immediately collapses. Here is what actually happens in that fraction of a second. The motor driver starts reading data before the IMU finishes its calibration. Because the initialization isn't synchronized, the leg controller sends invalid targets to the motors. You press the emergency stop, but the motors keep running because no specific node is listening for a coordinated shutdown. To prevent this, production robotics use ROS2 Lifecycle Nodes. Platforms like the Boston Dynamics Spot use lifecycle states to coordinate hundreds of subsystems, ensuring every sensor is ready before any movement is authorized. Without this coordination, nodes race against each other, hardware gets damaged, and safety systems fail. Enforcing an ordered startup and shutdown through a strict state machine is the foundation for keeping physical hardware operational. At 0 milliseconds, nodes boot into an isolated, unconfigured state. At 5 milliseconds, the lifecycle manager configures base-level hardware. By 30 milliseconds, nodes connect into a safe, inactive status. At 60 milliseconds, it calls Activate, and the system safely begins running. Notice the exact separation of responsibilities here. A configured state means the software has successfully connected to the physical hardware. An active state means the hardware is authorized to move and publish data. Convert to a lifecycle node by updating dependencies. Move all device initialization into an onConfigure method, and crucially, return success so the boot sequence continues. By deferring the hardware connection until the manager asks for it, we expose connection errors immediately. If a cable is unplugged, the manager catches the failure during onConfigure and halts the process before the robot ever tries to move. Lifecycle nodes need a conductor to tell them when to transition. Enter the Lifecycle Manager. In this YAML file, Level 0 contains IMU and motor drivers. The manager holds the Level 1 leg controller unconfigured until Level 0 successfully boots. We establish explicit dependency levels in text, and the system enforces them in practice. This replaces a chaotic race condition with a deterministic boot order. Open your terminal and type ROS2 Lifecycle Get with the node name to verify your motor driver is squarely in the active state. State management is also critical during runtime. If a motor begins overheating during operation, we need to intervene immediately without shutting down the entire robot. Monitor the transition topic in real time. Instead of an e-stop, manually deactivate the motor to cool off. Once safe, type Activate to resume the task. We diagnosed a hardware issue, safely powered down the affected component, and brought it back online. The main computer never rebooted, and we never lost our sensor data. You've just replaced a fragile initialization script with a production-ready, fault-tolerant state machine. Whether it's a research quadruped or a massive industrial fabrication arm, the requirement for absolute control over hardware states is identical. This architecture is the standard for managing complexity in heavy industry. Utilizing ROS2 lifecycle nodes ensures safe hardware initialization, enforces strict software dependencies, and allows for surgical recovery from physical faults on the fly. Your next step is to convert the remainder of your hardware drivers into lifecycle nodes and map out your own dependency YAML. Check the description below for code snippets on advanced emergency shutdown patterns and start building robots that survive the real world.